Good afternoon, and welcome to the 13th session of the Fall 2017 Sunoikisis DC semester, which is focused on digital cultural heritage. Today, Yanne Broux from the University of Bordeaux and Horne from the University of Pittsburgh join us, and they will have a lecture on network analysis and visualization. So please, Ryan.
All right, hello, and I'm going to start out the lecture with just a brief introduction to network analysis, some of the terms and concepts. And just so you know that we'll be starting with looking at Gephi, which if you're following along, you can install yourself. It may crash early, it may crash often. That's part of the fun for network analysis. Yeah, so, just so you know, we'll be starting with. Yeah, so don't worry about it if it crashes. Just begin with. Again, this is a very quick introduction to social network analysis, and let me get my screen shared. There we go. And again, the overview, we'll be using Gephi, and I'll go over some data best practices and some discussion of network terms and concepts. So the basic idea for networks is that they're a collection of stuff. So whatever it is you happen to be studying, this could be people, these could be locations, these could be concepts. Really, it's whatever it is, and that some of these things are linked together. So we could think of, say, this workshop as a network, that we're all peoples, we're all entities, we're linked by being in this workshop. You could think of different kinds of groups within it. Maybe some of us prefer, say, cold beer to beer that is at room temperature. Those would be different kinds of links. And so you can see this is a very flexible definition. There's all kinds of subject domains that can go on to this. But really, before you even begin considering networks, you have to think about data and what your data is and what it is that you're looking at. So to begin with, like, what is your data? So if you are conducting network analysis, if you have a bunch of stuff, the first thing you need to say is, well, what is this stuff? And then how am I going to organize it? And what am I trying to show? And so this gets to a lot of ideas of, like, say, database design. We're not going to get into that today, but you should be thinking of your stuff as data. So if you are, say, an archaeologist, you might want to start thinking of your places as data. You might want to start thinking of, say, interactions between different people or organizations as data. And like, say, 99.9% of all digital humanities projects, you probably want to start with something like a spreadsheet, where you just fill out, okay, here's one thing, here's another thing, and so on. So in this instance, like, if you were going to look at, say, people, each person would be on a row with some defining characteristics. And what do I mean by that? And this is kind of a wordy slide, but the idea is that you need to have some just best practices for whatever it is you're studying. So for people, you want to probably have a unique identifier. So think of this as kind of like a serial number. It's something that is unique and something that is arbitrary. So for people, you don't want to use their names. People may have the same name. For places, you may want to use something like, say, a Pleiades ID as a unique identifier, or make your own. It's completely arbitrary, but it needs to be unique. And then what you need to do is have each column in your spreadsheet has the same kind of data. So if it's a name, it's the name the whole way down. If it's, say, the location or coordinates, it needs to be the same the whole way down. And the idea here is that you can have as many of these columns as you want. So if you're studying people, you can have name, a gender, affiliation. It doesn't matter. You can have thousands of additional columns, but they all have to be kind of the same type. And that's just really how to start thinking about your data before you even begin thinking about it as a network. And then once you're ready, you have some of your data formatted, you may start thinking, well, what is social network analysis? How does this help me? And the basic idea is that we're looking at how our data relates to itself. And so how is this big list of stuff that we've just generated, how does it connect it? How does it actually associate with each other? And once you start doing this, you may see, there's networks all over the place. I see connections everywhere. One of the readings for this workshop we have is when not to use networks. So it's really kind of an interesting thing of once you start playing around with network analysis, you can see, well, this would be good for a network, this wouldn't be good for a network, and a lot of that just comes with experience. And then, again, networks are these entities. They're linked, and there's a lot of different measurements. We're going to go over some of those in a few minutes. And one of the really powerful things for this is the potential for visualization. That networks, you can see this visualization, you can see a lot of these connections in ways that you normally would not be able to do. And so when we do this, when we make the networks, again, we can use this for people, concepts, there's this for literature, biological systems, and for, say, electronic systems. And so this would be an example of a biological network. This is actually like a genome mapped out. So you can see it's a network. There's things that are interacting with each other. You can see this is probably a network that's familiar to most of us. This is Facebook, and it shows just the friendships between people put onto a map. Again, another use of a network. Or say, this is another one. This is the Game of Thrones, and it shows you when two characters are talking to each other, and those are all the connections, showing you that probably Tyrion is the main character of Game of Thrones. And so, just to show you some terms, so you know what we're talking about, the most important ones are nodes. This is the stuff that we're looking at, the entities. So these are the circles on the graph. These could be, again, the people. These could be the places and the locations. And so just think of a network, nodes as circles. This is our stuff. And you may see the term actors used as well. And these are just referencing nodes. I prefer the term nodes because it takes no real assumptions about agency or action on the part of the node. So you may see actors, but nodes are generally the terms that we use. And then edges are what links our stuff together. And edges can be anything. These can be biological relationships. So you're making, say, networks based on who's a parent of whom, who is a sibling of whom. It can be, say, edges for this workshop. We're all participating in it. It can be edges of maybe you're all fans of the same sports team. Maybe there's an intellectual edge that you're all thinking about the same thing. It really can be anything. And these are represented by lines. And so when you put this together, you have really two kinds of graphs. The first one is called an undirected graph. And this just shows that things are related to each other. And this is really the default for many, many networks. And an undirected graph looks, again, something like this that we just saw before. Here we're just showing that people are connected. We're not saying that there's any direction to it. So we're not saying that, say, that Sansa and Tyrion, there's some kind of power relationship. We're just saying these two characters are connected in some manner. And so that is what we call an undirected graph. There's no arrows, just two nodes, just any number of nodes, any number of connections. Now this is a directed graph. And as you can see, there's arrows that actually show on the edges. And these are showing a direction of relationships. So for these, you would think of something like, say, biological relationships. You'd probably want to show a directed graph because you want to show parents of somebody, relations of somebody. This could be very useful for other graphs as well. If you have, say, alliances you want to show allied with or hostile towards or subordinate to, you're going to want to have directions. And that's what these arrows represent. And so once you start getting into directions, you start getting into measurements that you can do. And so one of the most important ones is called degree, and that's the number of total connections to a node. So in our example here, the node artist would actually have a degree of 3 because table 1, table 2, and table 3 are connected to it. So that's just how many connections are on a node. That's all that degree is. For another measurement, though, n degree is the number of connections pointing to a node. So in our example here, artist would have an n degree of 2 because table 1 and table 3 both point towards it, while table 2 would have an n degree of 1 because artist points towards it. So you can see that once you have a directed graph, these are a couple different measurements you can do. And then we have something called out degree, which is the number of connections pointing from a node. So again, in this example, artists would have an out degree of 1 since it points to table 2, and table 1 and table 3 would both have an out degree of 1. And so again, this is showing you what directional things can do for measurements. And this becomes important, as you could imagine, if you're trying to say, well, what is the relation, say a location, how much stuff is coming into it, you want to know, say, an N degree. If you're looking at, say, a network of production and you want to see how much stuff is going away from a certain area, then you'd want to have its out degree. And so that's why you want to have these kind of measurements. And then you have something called weights. And this, again, can be anything. So a weighted degree, in degree, out degree. If you have, say, a lot of stuff coming in, if we have a location where, say, it's getting a bunch of goods from another city, we can weight that. We can say, you know, there's 50 pounds of stuff coming in. There's 50 tons of stuff coming in. These are all different weights. Another way to think of it is, say, sports fans. You may be a sports fan 100% of the time. You've got, say, Arsenal socks on, and you're always for that team. Or perhaps you're a sports fan a quarter of the time. That would be different weights. One who is a sports fan all the time would have a weight of 100. One who's a sports fan, maybe in the playoffs would have a weight of, say, 25. And so for the example I'm showing you here, this is an example of talks, and the weights of the different numbers here are the percentage of time that each one of these talks discussed community life. So you can see that, like, say, table 2 up here in the red only discussed it 1% of the time, while the two tables in purple discuss this concept 6% of the time. And different weights are traditionally shown by thicker lines. So the thinner the line, the smaller the weight, thicker the line, the larger the weight. And these are just, again, ways for you to look at a graph and figure out what's going on. Before we get into any of these other things, I want to show you how this works practically. So if you're putting your data together, and you'll probably want to produce things like, again, spreadsheets. So if you have, say, a nodes table, let me just import that for a second. You'll see that you'll have an ID. In this case, it's very arbitrary. A label, so something human readable, and that's all your nodes table really has to be. This is a table that shows talks, where I was looking at concepts, and then the table themselves. So there's only really two kinds of nodes here, concepts and the table. And your nodes list, again, just lists all of your stuff. While your edges list, bring that in, lists just as two sources of IDs. So we're saying that this table discussed this topic, and so on. And that's all that these two things need to look at. So when you have these, just again, a spreadsheet that gives you all of your stuff, and then a spreadsheet that just has your two IDs together, that's something that you can bring into Gephi and to Cytoscape, into actually any program that you want to build a network. So in this example, we'll just bring it into Gephi, and hopefully it won't crash. All right, it didn't. And so what you would do is say, well, I'm going to go to my data lab here, and I'm going to import all of my nodes. So I'm bringing in all of my list of stuff, and just finish it all up. And Gephi likes to tell you that there's no errors, which is reassuring. And you'll see that my spreadsheet's now in here. And if you'd go to overview, you would see just a bunch of dots. And so these are all the things that are on my list, but there's no connections. So then we'd bring in our little spreadsheet, which has our connections on it. And then you would see all the nodes now have direction, they all have connections. And really that's the basics of making a network. It's just making your list of stuff and then another list that has the IDs of the stuff and how they're related. And then once you've done that, once you've built this network, what you can do, let's see here. Is start doing some analysis of it and looking at how things are connected. One way to do this is paths. And this looks at how you can actually go through your network, how you can go from one node to another. And this is a design, and when you start designing your own networks, which for say an electronic version of that is a goal, a lot of networks want to have connectivity. And so as an example of that, I'll just let the question dangle there since I can't actually hear anybody. Does anyone identify this or know what this diagram represents? And I'll give you a second or two to look at it. This is a diagram showing. Yes, was that Tom? This is the early internet, and what it is a diagram showing you connectivity between different nodes, and that this was designed with the idea that if one node got taken out, the rest of them could still communicate, and that this is a goal of design networks, and that you'll find if you actually study human networks over time, it starts developing along the same lines, that there's redundant connectivity between people. And now, looking at all these different nodes, we've got, so I just showed you one about networks, I showed you one about people, one about conversations and people. And this brings up the thing about modes and types. That a mode of a network tells us what's in the graph. That I have a one-mode network, I'm only looking at people. I have a two-mode network, I'm looking at people and things. And then a type is just like, what am I looking at? Am I looking at an individual? Am I looking at a group? Whatever. And this comes to play when you think about how to actually analyze networks. That if you have a one-mode network, these are just about some relationships between nodes. So if I'm just showing people related to people, that's a one-mode network. And that's the same kinds of nodes, same kind of edges. And there's some differentiation allowed in edges. So I could say parent and child is still a one-mode unipartite network, because we're talking about people. If I start putting in different things, then it's a two-mode network. And so, again, their example here being a one-mode, people. A two-mode is different kinds of nodes. And this is actually very popular for historians. So you'll show that, like, say, people are connected to events, say that locations are connected to goods, or they're connected to alliances. And so a two-mode or multi-partite network, you're going to see a lot of these in historical study. You probably don't want to make a network that has more than two modes. You don't want to have people, ideas, and places all in a network, because then you start not being able to do network analysis very well with it. That most algorithms, most network measurements are designed for one mode or at the most two-mode networks. So just something to keep in mind, that if you start making networks with 3 or 4 different kinds of things on it, you may want to start splitting those up, because some of the network measurements just will not work. And so this would be a two-mode network where we'd have, again, users and groups, or you can think of this as, people and places, whatever, like 2 different kinds of nodes put together. And so another important concept is, once you start thinking about nodes and connectivity, is something called components. And that a connected component of a graph is an idea that every node has a path to every other node. So you can have a giant component of all these nodes are connected to each other, another component which has another group of nodes connected to each other, etc. And so you can think of, say, a graph that has 3 components as going to have 3 different groups of nodes that don't talk to each other. Or a graph that has one giant component is one group of nodes that are all connected in one way. So if we think of a giant component, we can think of, like, let's look at Game of Thrones. Everyone hates Joffrey. And that would be a giant component of the network, that if you're looking at who hates Joffrey, that's basically everybody, with maybe the exception of Joffrey himself. And again, most networks only have one giant component. Now, if we're thinking about historical networks, a really interesting thing comes to play, the merger of giant components. That if we think about how networks develop, that, okay, maybe these components start to coalesce, this can actually show sudden and often catastrophic change. If we think of humanity as a giant network, when the old world and the new world components merged into one, it was catastrophic. There was disease, political change, previous contacts were destroyed, And so you can see that if you have components, human components merging, this often means that something is going on. And this is something that you would map over time. You'd have, like, say, a network snapshot of 1 year, of another year, maybe a decade upon decade, and you'd start seeing relationships coalesce and these components join. There's probably something really significant happening. And this brings in the issue of time, and that time in networks, especially say in Gephi, it's really hard to show this. So you can start showing time, but it's a really messy thing that we're not going to get into too much today. If you want to also think about other kinds of things in networks, there's a concept of distance. And this is basically the path from one node to another, and that we can actually look at this for smaller networks, like, okay, 2 nodes, there's only a distance of 3 between them. But once you start getting into, say, hundreds of nodes with thousands of connections, you can see why we need computers to start computing the distance for us. And so again, a distance would just be saying, like, with node A and node B, how many steps are between them? So if we're thinking about, again, networks of geography, we could say, well, how many steps are between the connections of, say, Rome and some fort out in the middle of nowhere? Well, what's the path? What are the number of places you have to go to get out there? And then there's the concept of network density, which is the number of edges divided by your possible edges. And that plays around with paths too. You can have a lot of paths, you can have a very dense network, and then that shows that you've got a lot of connectivity. And this is one of the basic measurements in social network analysis. And it's really interesting if you're looking at, say, how diseases spread. So if you have a lot of very complicated paths, but not a very dense network, it's going to be hard for a disease to spread. But if you have a very dense network with a lot of paths, a lot of small connections, something will spread very quickly, like diseases, conspiracy theories. All these kind of things can spread in a dense, tightly packed network with small paths. So as you start looking out and seeing, oh, what's the connectivity of my network look like, you can see how these different things come to play. And then a final concept I kind of want to leave you with is this idea of centrality. And this is often what people want to see in networks. Who's the most prominent, who's the most important players in a network? And so the idea for this is, once you map everything, and you can do this in Gephi, and I'll show you in a second, you start saying, okay, well, who's the most important node? Who holds everything together? And so centrality is saying, well, how many paths go through this node to every other node? Is this node represent a key part of the whole network? And so to actually see this in play, what you would do is go to Gephi, and you would actually say, well, what's my path length here? And that actually gives you your centralities. So if I'd run it on my network here, it gives like the betweenness, which is, again, how many paths go through a certain node. So the larger the betweenness centrality, the more important the node is. And in a Gephi, what you can do is, if you go over to this strange looking thing here, it's your size, and you can size it by betweenness. And you would see, for this node, this network, there really isn't a really central important node. They're all about the same for betweenness. So there's really no one key in this network that's important. If it's a network of people, you may notice that one is more important than others. If you were going to do, say, the Roman Empire, you would probably see Rome as a giant node for betweenness, that a lot of things have to go through Rome to go somewhere else. And so those are just, again, some of the concepts. There's 2 other ones I want to leave you with before we discuss this kind of in terms of geography. Another measure is an interesting one that a lot of people get confused about, which is Becker centrality. And this is kind of interesting. It shows that basically you are important if your friends are important. So you might see this in certain publications. Let's say I have very few friends, but my friends are the president, the Pope, Santa Claus, and like the head of association football. I would have a high eigenvector centrality because all of my friends are very well connected. And this can really show you that you have a global importance, even though, say, you'd be looking at a graph saying, oh, he only has 4 or 5 friends. Locally, I might not be that important, but globally, because my friends are important, I am important. And there's a lot of math for this, but Gephi thankfully does this for us. And so you would just run, if you go over here, eigenvector centrality, and it tells you who's important. And then you can rank yourself by eigenvector. And you would see now that certain nodes are larger because their connections are important to the structure of the graph. And then another powerful thing is the idea of community detection. That when you have nodes, if there's paths and connections that are more dense between certain groups of nodes and others, that forms a community. And for Gephi, this is called the modularity measurement. And a lot of people make this the color of their nodes. So if we're going to go here, we'd say, well, what's our modularity? And using the defaults most of the time is acceptable. And then you would go to this little thing here that looks like an artist palette. And you would say, well, I want to color this based on my modularity class. And you would see Gephi has detected that the orange nodes are more densely connected. The purple nodes are more densely connected to each other, and so on. And so this is a good way if you have a big mass of data to start saying, well, here's a group, here's another group, and these are all, again, on density of connections. Now, what does this mean for us? Well, to show an example, this is a graph of everything in Pleiades, all nearly 40,000 locations, and we have this concept called connections. And that this is everything within Gephi showing all the connections. And you'll see that, say, Hadrian's Wall has a lot of things connected to it. The Mediterranean Sea has a lot of connections. Sicily has a lot of connections. And all this graph is just showing is what we as a group have said are connected to each other. And it's an interesting graph. It's kind of an intimidating graph, and it's really hard to read. But an interesting thing that you can do, there's a plugin in Gephi called geospatial plugin, where if you have your coordinates, you can actually map them all. So this is the exact same data, only just put on their XY coordinates on Earth. So it shows, again, connectivity, where things are located, and the sizes are based on centrality measurements. So this shows Pleiades as a network system. And this is something that's really interesting and kind of on I'd say the forefront of social network analysis. Is putting your stuff, getting XY coordinates, putting it on geography, and seeing how those influence each other. And for a more, say, manageable example, you can do something like this. These are all, excuse me, it says it loads up. These are all the little fortresses of the Peloponnesian War and how they're related to each other. And I put them into Gephi and made a network. And Gephi said, well, here's our communities. So the purple communities are better connected to Athens. Green ones are connected to Sparta. It said that these orange ones are a community themselves, and it identified ones in Sicily as another community. And that for here, identified things, red being hostile, blue being peaceful. And you can see, well, here's all the connections Athens has to different locations. And here's the connections that, say, Sparta has to different locations. And so this is actually a somewhat comprehensible, interesting graph. But however, if you're still doing this kind of thing, what you can do is put a whole bunch of entities on a graph and have something that just doesn't work at all. We did this for the Gospel of Luke, and we call this the flying spaghetti ball of doom. And as you can see, we're trying to say, well, here's entities that are locatable. Those are the ones in white. And the ones that are bouncing all around the screen are things that have no geography. This kind of thing is really hard to see and hard to analyze. And so if you're interested in bringing together networks of geography, this is really something that we're struggling with, something that we're working on at the moment, and something that I encourage you to help contribute to. That this kind of thing is interesting, this kind of thing is hard, but it's there. So let me close all that. And stop the screen sharing, if I can. And so that was a very, admittedly quick and kind of comprehensive overview of what network analysis is. You should be, now familiar with what nodes are, what edges are, what connections are, and where some of the usefulness of putting it, say, into a geographic context is, and where some of the problems are as well. And so hopefully you're not thoroughly confused about what networks are, or about what these concepts are, and I'll hand off the discussion.
Okay, great. So I'm going to take over here. Let's just get my screen started. Okay, so hi, I'm Yanne. I'm going to show you some examples of how I use network analysis in my research. Maybe just a little bit of background about myself. So I'm an ancient historian, a papyrologist to be more precise. So I had no training in digital humanities whatsoever. I just kind of rolled into databases while working on my PhD. And then as a postdoc, I discovered network analysis thanks to a colleague of mine. So just to say that you don't need a technical background to get started with this stuff. We also started up a blog where we explain some basic stuff about network analysis and how to work with Gephi. The address is on the slide. Because when we got started about 5 years ago, there was almost no support for people in humanities. Fortunately, things are much, much better now since network analysis has actually become relatively popular. But the blog is still there, so if you want some more information, you can always check it out. Another thing, so the examples I'm going to show all come from data in Trismegistos. That's a large portal that collects sources from all over the ancient Mediterranean. But I mainly work with the people database, which is still limited to Egypt. So the examples I'm going to show you today focus on Egypt. So the first network I wanted to show you is like a network I experimented with when trying to learn network analysis. It's nothing spectacular. It's just a tiny example of how networks can show things you normally don't see when you're just reading the sources. It's based on the Zenon archive. So Zenon was an immigrant from Caria in Asia Minor who became the manager of a large agricultural estate in the Fayum region in Egypt, which you can see here on the map. This estate was owned by Apollonius, who was the finance minister under Ptolemy II and III. So we're talking 3rd century BC here. And this Zenon, he compiled an archive of some 1,800 texts. It's one of the largest archives we have from Egypt. And almost 5,000 individuals are mentioned in these texts. And these texts are spread over more than 30 years. Now, if you make a network out of all of these people, you get this. This looks really cool, but there's nothing much you can do with it. It's just like this huge jumble from which you can't read a lot, except perhaps that Zenon is the big blue node in the middle there. Another problem with this network is that it's static. So it incorporates text from a really long period, well, a relatively long period. And so relationships that actually take place at different intervals are presented as simultaneous here. So it's not really a useful network. So that's why I split the archive up into smaller time periods. And I also focused on letters only, since this type of text contains the most evidence of direct relationships between people. And so I created two small networks. The left is a network of Bonakistor, who was Zenon's predecessor. He ran the estate the year before Zenon came. And then the right network represents Zenon's contacts during the first year that he was manager of the estate. And by working this way, you can kind of start comparing these networks. So, for example, I took a look at the density of the networks. Like Ryan already said, density measures whether there's much cohesion in a network, and it's normally expressed by a number between 0 and 1. 0 meaning that none of the nodes are connected, and 1 meaning that each node is connected to every other node. So Bonakistor's network has a density of 0.1. This means that 10% of all possible edges are in fact present. And this is considerably higher than the density in Zenon's network, as you can see, which is only 0.043. And when you compare the graphs, as you can see at first sight, Zenon's network seems more connected, but this is merely because of the size. There are 115 nodes in this network, and there are only 60 nodes in Bonacestor. So that's why Zenon's network seems a bit busier. But when you remove the two main protagonists, you see that Zenon's network to the right actually falls apart in a lot of small components. You still have this limited giant component in the middle, but the rest are all really small, unconnected components. In Bonacestor's network, however, most of the network actually stays intact. So it means that a lot of the people in this network interacted with each other directly without needing Bonacestor as an intermediary. And this could have something to do with the fact that Zenon was new to the job, that he was still building up his own network of employees, that he didn't simply take over Bonacestor's network. Or perhaps that he was just a greater control freak than Bonacestor. We don't really know, but it's a nice way of showing the difference between the two. So this was just a small test case I did when starting out. Since then, I've been experimenting with other types of data where network analysis can be helpful. I've worked with networks of place names, for example, but since Ryan has already talked about that, I'm not going to go into that further. One of the main things I use networks for now is onomastic analysis. Much of my research has focused on personal names, and network analysis can provide us with some clues on how ancient names were perceived by the people who use them. Studying network names from a network perspective allows me to look at family traditions and naming practices on a larger scale, so not just within a single family, but within larger communities. And it allows me to discover how important the language of a name was at this time. So if people with Egyptian names were more likely to give their children Egyptian names as well, things like that. So this is an onomastic network. So it's a network of names, names attested in texts from an Egyptian town called Hermopolis. And you can see Hermopolis here. It's somewhere in Middle Egypt, right along the Nile. And chronologically, we find ourselves around the beginning of the 2nd century AD, so well into the Roman period. But despite this, we hardly see any Latin influence in the naming pool here. So I've colored the names according to their language. Green nodes are names of Greek origin, blue nodes are Egyptian, and Latin names are yellow. And you'll probably have some trouble finding the yellow nodes. There's one here, a Cornelius. There's a Justus up here, and then there's a Fronto down there, but that's about it. And then there are also some gray nodes in there. Those are names of unknown origin. Now you can find an interactive version of this network online following the URI here. It takes some time to load though. There it is. First thing though, that the colors used in this network are slightly different. So Latin names are orange here, but that's explained here in the legend, so you can read that. This network allows you to zoom in and to click on specific nodes to get some more information about different properties and see what names they're connected in. You can also search for names, stuff like that. So I'm going to stick to the PowerPoint since that way I can show some additional info on the screen, but feel free to play around with it if you want. So where's my profile? Okay. So the edges in this network are defined on the basis of genealogical relationships. So they are directed networks, which means that there's a link from name A to name B if a person with name A chose name B for his or her child. So it may be important to stress here that the nodes represent names, not individuals. So each name has only one node in this network. And two names are linked if they appear in the same nuclear family. So, for example, if there's a Betelgeuse son of Pachumis, there's a link from the name Pachumis to the name Betelgeuse. And if someone totally unrelated to the previous individuals is also called Betelgeuse, but he's the son of Horus, then there is a link from the name Horus to Betelgeuse, and so on. So Ammonio, son of Horus, you have a link like that, and so on. And then the network is also weighted, so because it's possible that there is more than one person called Horace who named their son Visualisation, for example, so then the arrow is thicker. And the size of the nodes is determined by their in degree, so the number of incoming edges. In an onomastic network, a high in degree is an indication of a name's popularity, since the more incoming edges a name has, the more often it was chosen by parents for their children. And so here you can see the 10 most popular names in the network. Hermaios, way at the top there, for example, comes as no surprise since Hermes was the patron god of the city of Hermopolis. So we have a lot of people called Hermaios. Now you may have already noticed when looking at the colors that the network is almost neatly divided into two sections. We have a predominantly Egyptian one, the blue one at the bottom, and then a predominantly Greek one. And this is already an important clue since it shows that people with a Greek name tended to stick to Greek names for their children, and the same for people with an Egyptian name. As you can see from the small table at the bottom, the Egyptian component is larger than the Greek component, yet the Greek component has, in comparison, has more edges, which means that it's actually more connected. And this is confirmed when we look at a measurement called the clustering coefficient. This is another way besides density to measure cohesion in a network. And what the clustering coefficient basically does is calculate to what extent the neighbors of a certain node X are connected to each other. Again, you get a figure between 0 and 1, whereby 0 means that none of node X's neighbors are connected to each other. So they're only connected to node X itself. While local clustering coefficient of 1 implies that all neighbors are connected to both X and to each other. So this local clustering coefficient is calculated for each node in the network, and then an average is taken for each component here. And it turns out that in this network, the average clustering coefficient in the Greek component is almost twice as high as in the Egyptian component. So this is another important clue that people with names in the Greek component tend to stick to a smaller naming pool for their children. And other properties in the network point in the same direction. So there are, for example, more ties with a higher edge weight in the Greek component. There we have 11 father-son combos that appear more than once. And one of them for the name Ammonios is what we call a self-loop. So there's a father called Ammonios who named his son Ammonios after him. And in the Egyptian component, there are only 6 of these combos with a higher edge weight. Reciprocal ties are also more common in the Greek component, indicating that names were sometimes passed down from grandfather to grandson. For example, Serapion, son of Eutychides, grandson of Serapion. So these are all indications that families that use Greek names were more traditional when it came to name giving, and that they chose from a more limited pool of names. Now, in the end, it turned out that the dichotomy that's visible in these two clusters here is actually a reflection of social status. So the Greek component reflects naming traditions of the local elite, while the Egyptian component reflects naming traditions among the peasant population. So the onomastic pool of these peasants was more varied, and the lower cohesion and reciprocity suggests that there was more freedom in the choice of names, that these people were less bound to status and convention. There's another aspect of these networks that I find more interesting, actually, and that's how these networks can give us an idea of how names were perceived by contemporaries. So in onomastic studies, names are generally classified according to their linguistic origins, as I've colored them here. But the form of a name does not always correspond to its social meaning. And the name Ezoeris is a really nice example of that. So it's situated at the top of the graph. And as you can see, it's blue. So it's an Egyptian name. It means the great Isis. But it's completely embedded in the Greek component. And the same goes for the name Isis itself. So although these were Egyptian names, they were not used by the population that would normally choose Egyptian names. But they were accepted by the local elite, which normally preferred Greek names as decent names. The opposite is also attested. So names that are Greek in formation but which are embedded in the Egyptian component. And many of these names, such as Hierex and Harpocration, that refer to various manifestations of the Egyptian god Horus. The Greek name Apollos, can also be seen in this light, since it refers to Horus's Greek counterpart, the god Apollo. So the Greek names in the Egyptian component all have a clear Egyptian ring to them, one way or another. And these are names that are generally not attested outside Egypt. So for the people bearing these names, there's a significant connection to their Egyptian heritage. So in this way, I think onomastic networks such as this one are very important because they show us that we should not simply take names at face value. Now, in another experiment of mine, I used networks to try and solve the problematic dating of some sources. The corpus in question is a group of demotic letters from Elephantine. This is an island in the Nile on the border between Egypt and Nubia. We have 146 letters that are dated to the 4th and 3rd centuries BC. Only 9 are dated to a specific year. So the majority is simply attributed to these 2 centuries in general. A lot of these texts do mention a regnal year, but they don't mention a ruler. So it's something like in the 5th year on the 6th month of Faofi, but whose 6th years this is, we don't really know. Now, a colleague of mine had a hunch that a significant number should be assigned to the middle or the second half of the 4th century BC, so around the time of Nectanebo II, so the last pharaoh of the 30th dynasty, and the beginning of the second Achaemenid period. But we had no evidence whatsoever for this. So what I did was first look whether people that appear in one of the texts that are dated to a specific year are also mentioned in other texts. So I made a network for this by connecting people who are mentioned in the same text. So the first network I got looked like this. Basically, every cluster in this graph represents one text, and the nodes are the people in the texts. Now, as you can see, the 2 clusters in the middle, they have green nodes, and these are people of whom we know that they lived around the middle of the 4th century. So the idea was to see if I could spot these people in some of the other clusters here, because if this was the case, the date of those clusters could be narrowed down as well to 343 or something like that. I found quite some people that way. So this other network highlights 4 reoccurring names before I added those clusters together. For a lot of attestations, we also had fathers' names. So in most cases, it was pretty obvious that we're dealing with the same individuals. And this is what the network looked like in the next stage, when some of the people highlighted on the previous slide were merged together. So you can see that there are much less smaller clusters and that we have this giant component emerging in the middle. I then again highlighted some other names that reappeared. So those small clusters with the colored node eventually became connected to the large cluster in the middle as well. And at this stage, we can say that all people in this large cluster can be dated to roughly the middle of the 4th century. And therefore also all the texts these people are mentioned in. Now, I wanted to go a little further than just narrow the date down to the 4th century, because some of the letters are dated to year 19, and it so happens that Nectanebo was overthrown by King Artaxerxes III in his 19th year. So I was wondering if I could somehow try to link texts dated to year 19 to texts of which we know that are dated to the first year of Artaxerxes III. And for this, I experimented with something that Ryan warned against, and that is 3-mode networks. As Ryan explained, 1-mode networks contain relationships between one type of node. 2-mode networks go a step further and include 2 types of nodes, as in this example, where the white nodes represent people and the black nodes represent committees. And so in 2-mode networks, nodes of the same type are never linked. So people can only be linked to committees, never to each other. But so I went a step further and went for 3-mode networks. And as you can probably guess, a three-mode network incorporates three types of nodes, in this case, people, sources, and regnal years. And thanks to this structure, I could try to see whether people that appeared in texts dated to the first year of Artaxerxes are also attested in texts that are dated to year 19, which would provide some form of proof that this is year 19 of Nectanebo. And so that the letters from Elephantine attest to the very last years of his reign. And that's why it was so important to carry out the identifications in the previous networks, because those people form the crucial link in this three-mode network. Now, the properties of a three-mode network are a little different than that of a one-mode network. So in a one-mode network, if you're trying to establish whether there's a close link between two subjects, all you have to do is check whether there's an edge between those two nodes. In a two-mode network, you have to add an extra hop. So if we go back to this two-mode network for a second, there's no direct link between two people here, but two people are close if they are part of the same committee. So in a two-mode network, looking for close connections implies two hops. In a three-mode network, the number of hops doubles yet again, because to get from one date to another, I'm just gonna end my full screen because otherwise I can't use my mouse. So if you want to go from one node to another, say for example from year 16 here to year 17 here, you first need to pass through this text, which is dated to year 16, which mentions this person, who is also mentioned in this text, which is dated to year 17. Now to get to my my point with the year 19 and the year 1 thing. So here's year 19, I marked it here, and here's year 1. And so I calculated the shortest path between the two, and as you can see, there are 8 hops away from each other. And in a three-mode network, this is not very far, since, like I said, the shortest path between any two nodes of the same type is actually 4 hops. So the path goes through this text, which mentions Eschnupmetis, son of Esnebonichos. And this person is also attested in this text, which is dated to year 18, since it's linked to this node. That text mentions Neferpres, who is also attested in this text, which is also dated to the year 18. And in this third text, Neferpres is mentioned along with an Eschnupmetis, who is mentioned in a text dated to year 1 of Artaxerxes. I know this sounds very confusing at first, but it really does make sense if you let it sink in. As you may have noticed, the name Eschnupmetis pops up twice in this path. And it is very likely that this is actually the same person. So Eschnupmetis, son of Esnebonichos, and the Eschnupmetis here. Since this Eschnupmetis doesn't mention a father's name, I'm not 100% sure. If he is the same person, we can skip this middleman Neferpres here, and we can merge these two nodes. And then year 19 and year 1 are actually only 4 hops away from each other. So that would, of course, be much better. But like I said, I'm not 100% sure. So I'm reluctant to identify the two. But anyway, still, the two are pretty close connected in this network. So it does provide some indication that we are dealing with letters dated to the last years of Nectanebo II. So this is a very non-traditional application of network analysis, but I wanted to include it so you can see that you can really do a lot of things with network analysis if you get creative. So I'll finish the class today with something light. This is a network I made for fun, or actually it's a visualization of a database of editors of ancient sources. So it's actually a network of modern scholars. And I made this just to get an idea of the level of collaboration there is. So maybe we can go to the online version as well. There's also an online network for this one. Yep, there it is. So it's a really big network, this one. So two scholars are connected in this network if they ever published a source together. The size of the node is determined by the total number of publication of the individual, and the colors indicate a person's level of collaboration. It kind of reads like a heat map. So dark blue nodes are people who have never published a source with anyone else, while the dark red node here in the middle and the like orange ones, those are people who collaborated with the highest number of colleagues. And again, as with the other network, you can click on the nodes, and then here on the side, you get a little more information about them. I generally only show this network to papyrologists because the graph is actually rather confronting. So this big cluster here in the middle, the giant component, it mainly consists of papyrologists, so people whose focus is Greco-Roman Egypt. So there's a lot of collaboration going on there. There are some clusters of epigraphers as well here to the side. But most of the people working on inscriptions are actually these scattered, unconnected, dark blue nodes that surround the giant component. So there's a very striking difference here between the two disciplines, at least when it comes to publishing text. This doesn't mean that epigraphers are less productive. I want to stress that, because here you can see, oh, there you go. Yeah, here on the side you can see some really, really big dark blue nodes, which means that they have a lot of publications. But they're kind of lonely. So papyrologists love this network because they say it proves that they're more lovable. And I have to agree, of course, since I was trained a papyrologist myself. So yeah, those are like the three examples I just wanted to show you for the class today. And I hope it was inspiring. So yeah, that was it.
Thank you, Yanne. Maybe do you two want to explain the exercises a bit for the students, the exercises on the GitHub? It could be useful if you say a couple of words on them.
Yeah, sure. Let me just get to the page.
When you do, you'll find that I incorporated some late-breaking alternative or additional step from Ryan. So number 3 is probably where you want to hand over to him. But otherwise, 1 and 2 are what you had, Yanne, yep, with a caveat that Ryan wanted to add about Java Virtual Machine.
Sure, yeah, okay.
Yeah, well, I can say a little bit about the first one. You want to download and install Gephi. And one thing you may encounter is that a lot of people do not have Java installed. And so you'll have to install Java as well. And when you're doing this exercise, I recommend that you download and install the Java development kit, because that seems to work better with Gephi than the Java runtime environment.
Is it so much of a problem? Because I thought with the latest version that it was solved. But
it's helped-ish. There's still... this is one of the, as you'll notice, this is one of the fun things about open source software is that it works sometimes, it doesn't work other times. So yeah, Gephi is improving in stability, but as I'm sure my colleagues can tell you, it's still, there's times where you will start screaming at the computer and wondering why everything has crashed. So when you are doing these kind of exercises, save all the time.
Yeah.
Like, make a change, save it immediately.
Yeah.
Maybe step away from your computer and come back, try it again. But yeah, go ahead for I guess your stuff.
Yeah, I when I tried to go to the GitHub page, I keep getting error messages. So I don't know what's wrong there. So the first example I found was just this really short exercise, and I think it's kind of fun for people to use because it starts from their Facebook pages and it's really recognizable. It's not ancient data, but it's just that it's easy to see the different components of your network and you can relate to it because it's your own network. The second is a more extensive exercise. It uses two data sets by Martin Grandjean. It's about the League of Nations, so the predecessor of the European Union. And he, step by step, he shows you what you can do with Gephi with these different types of networks. And he even shows you how to change from a 2-mode network to a 1-mode network, for example, stuff like that. So, yeah.
And then the third exercise is going to involve a little bit more work on the student's part, where you have to go to different Wikipedia pages, find out what they say about the Peloponnesian War, and basically sketch out the and part of that is to make your little tables, see how people are connected. And the fun part of this is to see how badly Wikipedia has gotten it wrong, or how right it actually is. So you'll see your networks, you'll see who's related to who, and that's a good way to actually check, say, Wikipedia articles, is by building a network and saying, nah, that's not right. I did something with Hellenistic people, and some of the connections just simply are not correct. And so this is, and sometimes amusingly so. And so this is an exercise for, say, students to both check their sources to build a network, and perhaps to contribute back to Wikipedia if they've gotten it wrong.
Yeah.
Yeah, and again, all those exercises require Gephi install, and hopefully your Gephi install will go well.
Yeah.
So good luck.
Okay, I've checked the YouTube page. We don't have comments, questions, anything there. So, Tom, if you have any questions.
I'm much better informed about network work than I was when we went into the session, but I don't have any specific questions. Just thanks for helping me get my head around how this works.
Sure. And one thing I think we should stress for this is both from the work that was shown here, some of the work I'm doing, and other people are doing, there's a lot of interesting things you can do with networks. It's not just people. It's not just places. You have names. I've done stuff with concepts of how people are just thinking about the same thing. So there's a lot of different stuff that you can put into a network analysis, and a lot of interesting ways you can break network analysis. But these are really, at the very least, are very powerful ways of visualizing connections. So even if you don't do the steps of finding communities or doing, say, eigenvector centralities, just visualizing how things are put together is probably, if you take nothing else from this workshop, I would say networks are useful for visualizing how things are related.
Yeah.
Yeah, true. But I think that the examples you've offered prove that networks are useful for more than that, for more than visualizations, because you can actually see patterns in a different way. I'm sort of a fan of network analysis. I mean, I think if used responsibly, it's very useful. And you generally have to explain this to people who generally do ask, why do you do this? Is this really useful? That yes, it is, because you do not see all connections and patterns as a software does, obviously, because you are not a software, you are a person.
Yeah.
So I think in this regard, this was a very useful session, because you've explained very well the theoretical and methodological part, and you've offered examples which will surely be useful for anybody who wants to get a better idea on network analysis.
Thank you.
Okay.
Okay. So this might be the first session this semester in which we managed to finish up on time. So once again, this was a very, very well prepared session, because so if this is it, thank you everybody for watching us. Thank you very much, Yanne and Ryan.
Thank you.
And
Bye.
have a nice evening or a nice day, everybody.
All right, you too.
Bye.
Bye.